So welcome everybody to the Logic Colloquium. It's a real pleasure to have Tyler Markkanen here today. So Tyler is as someone mentioned a little while ago, he's kind of an honorary member of the Logic group. He was a grad student at UConn, so he was for a long time a member, but he never left the group in some sense, because at least when we used to meet physically in the olden days, he would show up at every meeting. So he's still part of the group, and most of us who attend always see him there. So if you do attend in the future, you'll see Tyler a lot. So it's a pleasure to have him here speaking this time. He will tell us about computing perfect matchings in graphs.
Yes, thank you, Demir. And I actually wanted to start with a plug. So there are two open positions in computer science here at Springfield College, and if you happen to have any friends in in computer science who are on the job market this year, please let them know. You can go to springfield.edu/human resources for more information. All right, that's the advertisement. This is joint work with Stephen Flood, Matthew Jura, and Oscar Levin. And all three of them actually have UConn ties as well, which is nice. And I figured I would kind of go backwards through the title. So it's computing perfect matchings in graphs. So we'll start by defining a graph. That's just a pair of sets. So V of vertices and E of edges. You can think of the vertices as points, edges as lines connecting the points. Technically, edges are sets of two vertices. And we say a matching is any set of edges as long as no two edges are incident with each other. And so, for example, this here in green is an example of a matching in this graph. No two green edges share a vertex. But if we included that edge there, that would no longer be matching. And to try to improve the matching, we have this notion of an augmenting path, an M augmenting path. And one of the goals is going to be to try to maximize the matching in the graph, see how many edges are possible to include in the graph with this property that they don't have any common edge. So again, the green edges are the matching. An augmenting path is, first of all, an alternating path starting outside the matching, not being part of the support of the matching, not being a vertex that's incident with any of the edges. And then switching back and forth between not being in the matching, not being in the support of the matching versus being in the matching. And so just as an example, this highlighted part is an augmenting path. It starts outside the matching, and the edges, I should say, on the path switch between not being in capital M and being in M. You can also start out, so that's one option. You can be an infinite path in that way, to be an M augmenting path, or you can start outside the graph, be alternating. You always have to be alternating outside the matching at the edges, or outside, inside, outside. But you can be finite as long as you end outside. So these are the two possibilities for M augmenting paths. And the useful thing here is that they augment, they improve the matching. So if it's kind of a neat thing, we can kind of switch the edges on this highlighted path, and it will maintain the support. So all the vertices that were matched originally are still matched. And in particular, those top and left, top and bottom point on the left are still matched. But now we've been able to include at least one more if it's an infinite augmenting path. But in this case, we're able to include two more in the case of it being a finite path. And that actually winds up giving us a perfect matching in this particular example. So perfect matching is one where every vertex in the graph, every point in the graph is incident to one of the edges in the matching. I guess it could only be one of the edges in the matching because no two edges in the matching can share a vertex. So Steffens in 1977 gave a sufficient and necessary condition for a countable graph to have a perfect matching, and it was to satisfy this condition A. So condition A says that if you give the graph a matching, and you take a vertex outside the support, outside the vertices of the matching, then there is an M-augmenting path from that vertex. We'll see in a little bit an example when you wouldn't have that. You wouldn't have an M-augmenting path starting at a particular vertex. But this winds up being again necessary and sufficient to have a perfect matching, and we call this result of Steffens PM, perfect matchings, and we can look at the easier direction of why it's true. So let's assume there is a perfect matching in the graph, and we want to show condition A is true. We want to show that given any vertex outside the matching, let's say any vertex outside a given matching M prime, there is going to be an M prime augmenting path. So that's what condition A was saying. Given any matching M prime, doesn't have to be perfect. So because we do have a perfect matching, we know that no vertices are isolated. So we know S. So S is just some arbitrary point outside of M prime. We know it has to have at least one neighbor. If it happens to be outside, if S's neighbor V happens to be outside of M prime, then we're good because that trivially is an M augmenting path. It starts outside of, M prime augmenting path. It starts outside of M prime. It switches between being outside at the edges of the path, switches from being outside and inside because it never goes inside, and it ends outside. That was the finite option. However, if it's going inside M prime, we can imagine that is due to M, right? The perfect matching brought us, let's say, inside M prime instead of outside. Well, M prime, because it's a matching, now we're inside, that new vertex is matched to something else in M prime, just by the fact that we're inside this matching. It's all the edges of the matching. And now we are able to resort to the perfect matching M. So we just bounce back and forth between M and M prime. And so now this vertex this new vertex has a neighbor. That neighbor could be outside, in which case we're good. Again, that's an M prime alternating, it's alternating, but in particular augmenting, meaning it starts outside and ends inside. Or it could have stayed in M prime, in which case there will be an edge for that new vertex. By the way, that was why I assumed the edge coming off of S was from M, because we could be concerned that M might backtrack over the green, right? Green being the M prime, not M. But we know that that can't happen because we've assumed this edge is in M, and matchings can't have, again, the edges can't share a vertex. So we're sure that it's going to be distinct, and we would just iterate this process. That vertex is in M prime, so it has an edge, and back and forth we go. Now it has an edge, it's incident to an edge in M, and so on. And so this is the infinite option for M augmenting or M prime augmenting path. Right? So therefore, it satisfies condition A. All right, so that's kind of the easy direction. And the hard direction is where we were kind of motivated to get into reverse math, mostly from one project that has been worked on by several people, Simpson and Shore, on a result known as the Koenig's duality theorem for bipartite graphs. And so we thought, well, this, we were motivated to kind of find a kind of interesting graph theory result that was, hard to prove. And this direction, this other direction, if we assume condition A, why does it have a perfect matching? That seemed pretty tricky. And so I'm sort of a novice when it comes to reverse math, but we can at least say that the three of the most important systems in reverse math as we go up restrict the comprehension axiom of set theory. So recursive comprehension, so the recursive comprehension axiom, RCA naught, that allows us to have quantifier free, or sets that are definable with quantifier free formulas. Arithmetic comprehension axiom, ACA naught, that allows us to define sets using any finite combination of number quantifiers. And ascending upward, Pi1 comprehension axiom at the very least starts to let us define sets using set quantifiers as well. And there are two others that I wanted to mention, WKL naught and ATR naught, so weak Koenig's lemma and arithmetic transfinite recursion. These add specific axioms to their base system. Weak Koenig's lemma being the statement that any infinite binary tree has an infinite path, has a path. And arithmetic transfinite recursion, well, at least for now, we'll kind of say that they kind of bring ordinals into the into the mix. The results that are known and common to the lower systems, ACA naught and WKL naught, that we found helpful to calculate the strength of the result that we stumbled upon, this PM, perfect matchings, were that ACA naught is equivalent to the fact it also has its own tree equivalence. So every infinite finitely branching tree has a path, not just binary. And WKL naught, weak Koenig's lemma, is also equivalent not just to the binary version, but every bounded infinite tree has a path. Bounded meaning that there's a function so that given a node in the tree tells us an upper bound for the possible nodes that it can branch off to. And these helped us specifically show equivalences with kind of the analogous versions of perfect matching. So restricting now only to locally finite graphs where every vertex only has finitely many neighbors, and bounded graphs for WKL naught. similar idea as trees. There's a function. We assume there's a function that, given any vertex, gives us an upper bound of the neighbors that it has. And at least one of the major questions, I think, in reverse math in general is, once we've proven a theorem, right, we like to ask, did we need everything that we used in the proof, right? And one of the big components of Steffens' proof of his perfect matchings theorem used maximal matchings. And so while working on these equivalences, we were also trying at the same time to figure out where maximal matchings fell on the reverse math hierarchy. And so what is a maximal matching? Well, it's any matching that we were talking before about improving, right? Matchings, improving the support using augmenting paths. It's a matching that can't be improved in that regard. There's no matching whose support properly contains the support, the vertices that are incident with the edges in the maximal matching. There's no way to get vertices that were not already included in the original matching. And so as a corollary really to his proof, Steffens shows that every countable graph has a maximal matching. So now we've gotten rid of condition A, right? So condition A was giving us perfect matchings, but if we don't assume that particular condition, then every countable graph will have a maximal matching. And we'll call that MM, similar to PM, MM being for maximal matching. We'll call this statement MM. And we sort of, for our first kind of result that I would like to show you, we showed that maximal matchings, again, restricted to specific kinds of graphs, locally finite graphs, and is equivalent to perfect matchings for locally finite graphs and also respectively bounded graphs. That's not going to be the case when we don't restrict. Maximal matchings will at least be stronger than PM. All right, so we want to show this equivalence between maximal matchings and perfect matchings. Perfect matchings, well, if we think in one direction, if we assume maximal matchings, we want to prove perfect matchings, again, restricted to locally finite or bounded graphs. If we assume maximal matchings, we want to prove perfect matchings, we get to assume we do have condition A. We can imagine having a maximal matching in the graph. Because we know it satisfies condition A, we know that if we take any vertex outside the maximal matching, there's going to be an augmenting path. That would improve the matching, which is impossible because it's maximal. So in fact, if we assume condition A, the maximal matching we get is in fact the whole graph, or it matches the whole graph, it covers the whole graph. All vertices are a part of the support. So it's really the other direction, I suppose, that I wanted to show you, which is that if we assume perfect matchings, then we want to show maximal matchings. So we showed that perfect matchings for locally finite graphs or bounded graphs is equivalent to ACA naught. So in particular, we have, well, ACA naught or WKL naught, depending on whether or not you're using the locally finite or the bounded. And so ACA naught, again, tells us that if we have an infinite locally, or locally finite, if we think of it as a graph, but finitely branching tree, it can it can give us a path. It says that there exists a path for that tree. And so if we want to prove maximal matchings, then we're going to use ACA naught now because we're assuming PM, and we're given a let's say we're given this graph here, we're given some graph, and we want to build a tree, right? And starting at some root node. And we'll ask what vertex should we match to 0, right? So we'll go in order however the vertices are numbered. And well, it should be pretty clear, right? We should match it to 1. And so we'll record that in the tree that we're, at the, we'll call that level right above the root level, the 0 level, the level for the vertex in our graph numbered 0. We'll record that he's been matched by way of 1. Now, how should one be matched? Well, given we had no choice before for 0. Given how 0 is matched, we have to match 1 to 0, right? Because we can't match it to 3 or 2. That would be, we would have 2 edges that are incident with each other, right? So there's only one option to match 1, and that's according to 0. And we just work our way through. This is the procedure for building the tree that we'll apply a CA naught to. And we now ask, where does 2 get matched? So again, just going through consecutively through the vertices of the graph. Well, 2 can get matched in 2 ways, right? It can get matched to 3, or it can get matched to 4 without interfering, right? Without being incident to the edge we already have. And so we want to record both those options, right? So vertex 2 can be matched by way of 3, or it can be matched by connecting it by including that edge to 4. And so to 3, where would that be able to be matched, right? That could be matched, it looks like only to 2. I suppose we need to take into account which path we're on, right? So if we're on the path that matched 2 to 3, then 3 matches to 2. Obviously, there wouldn't be any other option there. And we should look at the other path too. That might give us another option, right? If 2 instead was matched to 4, could 3 have been matched, right? And if I've been explaining matchings correctly so far, it should be hopefully clear that 3 cannot be matched in this setting. And so we would, stop the path we'd stop that branch of the tree from growing. What about 4, right? Just continuing on through the vertices, just to complete this tree here. 4, we only have one option now for the path. We know that 3 is connected to 2, so 4 could only be connected. 4 could be connected in 2 ways. It could be connected to 5 or 7, right? Again, without interfering with the edge 2, 3. And so we'll record those. 4 can be matched to 5 or to 7. Those are 2 possibilities given the previous matching. Moving to 5, and we'll continue on through the procedure continues on through all the vertices. 5, again, we'll look at each possibility, each branch that we've created. So given that vertex 4 was matched by way of 5, where could 5 be matched? Well, it looks like, again, 5 cannot be matched. Can be matched, sorry, to 4. It can't be matched to anything else, right? Couldn't be matched to 6, that's for sure. But it certainly could be matched to 4. And what about the other branch? Okay, if 4 was instead matched to 7, 5 now, where would 5 match to? 5 could match now to 6. All right. almost there. So 6, where would that be matched? Again, we always want to look at our possible branches. So the left branch here, which matched 5 to 4, that where could we match 6? We shouldn't be able to match 6 anywhere, right? So that's one place definitely where we would stop the branch. But then we're now left only with one branch possible. So we no longer have to make choices here. 6 has only one choice. It has to be matched to where it already is matched, 5. And then 7, again, making sure that no green edges, right, are incident with any other green edges. 7, given the one path that we have now, the one branch, it can't be matched to 8. Can't be matched to 9. It's definitely matched to 4. I mean, that's one possibility. That's the only possibility. So we would match it to 4 because it already was matched. Again, moving consecutively through the graph, vertex 8, right? Because we only have one branch left, 8 has kind of no options. So we abandon 8, and he won't necessarily be the only one that's abandoned depending on the structure of the graph. But then 9, again, we have to keep all these choices now because we only have one branch. 9 is now going to get matched only to 10. And it would, if this spine kind of continues on infinitely, we see that it would just go on forever, matching every other. And so in particular, this is going to be a maximal matching. One way to kind of see that is that 8, and I said I was going to show you an example of a graph that doesn't have an M augmenting path, right? That doesn't satisfy condition A. So if you look, 8 doesn't have an M augmenting path, or M being the green vertex, the green edges. There is no way to start at 8 and alternate between green and not green edges and either go on forever, right? The only way to really go on forever in this example would be down here, and that wouldn't alternate, right? Would be outside and outside, or to be finite and end outside. But again, there's no way to do that either. So in particular, this doesn't satisfy condition A. So this isn't necessarily arguing in ACA not, but at the very least, we know because of Steffens' theorem, it's equivalent to satisfy condition A and to have a perfect matching. So we know because this doesn't satisfy condition A, it's not going to have a perfect matching. Matching 8 would be the only, well, matching 8, the 8's the only vertex that's not matched in this situation. So that would be, that would constitute the perfect matching. So therefore, this must be a maximal matching, right? There must be no matching that improves it. The only one would be a perfect matching, which we know doesn't exist. All right. So argument kind of half in, half out ACA not there. But this is at least hopefully giving the idea of how to construct the tree. And again, ACA not gives us a path through the tree, assuming we can prove that this is finitely, well, it's finitely branching because the graph itself is locally finite, and it's infinite. Assuming we can prove that, ACA not will give us the path, the infinite path, and that will therefore correspond to the maximal matching. Right? So therefore, PM implies MM, at least for locally finite, and similarly for bounded if we dealt with WKL not. The other kind of construction I wanted to kind of show you today climbs up kind of one more rung on the reverse math ladder and works with sigma 1-1 axiom of choice, which is kind of off the beaten path of the big 5 that we introduced earlier. But it is known to be strictly between 2 of the big 5. ATR not implies the sigma 1-1 AC not, which in turn strictly implies ACA not. And one of the reasons we also were kind of encouraged with this perfect matchings is that it wound up having kind of being a good example for the individual levels of the reverse math hierarchy. In particular, we now are turning to full perfect matchings, full PM, and want to show that that implies sigma 11 AC naught. We'll use this known equivalence to this sigma 11 AC naught, which is that if this is in the Simpson text for reverse math. And so it says, given any sequence of trees, t sub k, so that each tree in the sequence has a path, an infinite path, there must be a sequence of g sub k's, which choose, each gk chooses one of the paths from each of the tks. And so we're going to try to use this equivalence to prove over RCA naught that our principle, the perfect matchings theorem, implies this system of reverse math, sigma 11 AC naught. And so we want to be now given a tree or a sequence of trees. So before we were given a graph and we wanted to create a tree, right? So at the very least, we can see from a logical perspective, we're flipping the script, right? And we're now being given a tree and we're going to produce a graph. And therefore we can apply PM. If we now have a graph, we can apply perfect matchings on that graph to hopefully pick out the paths in the tree, in each tree. All right, so once again, I just think it's kind of a nifty procedure. And actually we didn't come up with this procedure. This was in a paper by Aharoni, Magidor, and Shore. This was one of the papers involving the Koenig's duality theorem for bipartite graphs. And they show this particular construction, where if we're given a tree, so we have the sequence of trees, TK. By the way, I guess I should have said what a tree was. So a tree is any connected, well, we can think of it as a graph, any connected graph. So meaning between any two vertices, there's a path, and it doesn't contain, that doesn't contain any cycles. So any way of going from one vertex back to itself by not repeating edges. But we are given a tree in this case, a sequence of trees, TK, and the part of the procedure involved is to create a doubling tree, or what we call the doubling tree. And so the idea is to break the tree into its levels. I mean, we're talking about levels in the last construction, and between, so we break the tree up into its constituent levels, and to each, in between each vertex that was once the same vertex, so these two vertices here, for example, we're going to add what we're going to call a doubling edge. And we'll also add a doubling edge to any leaf as well, upward, and include an ending node. And so why this is helpful, so I mean, this is a tree, but thinking of it now as a graph, if we first verify that it has condition A, we won't maybe talk too much about that right now, but apply the perfect matchings theorem, because again, we're trying to reverse perfect matchings to sigma 11 AC naught. And so we're trying to find or define the path through the original tree T sub k, and really all the T sub k's in the sequence. We're really going to take these TK hats, the doubling trees, disjointly union them so they're really one graph. We're going to apply perfect matching to that. And the real question is, what does a perfect matching do to the doubling tree? Why was the doubling tree important? Well, first of all, the root node, of course, if it's going to have a perfect matching, right? We apply PM. So we now have a perfect matching. We know the root node has to be matched, right? Every vertex is matched. So in particular, the root node. And let's say it goes off to the left here. I mean, we can look at the situation on the other side as well. Then this top node of the first doubling edge, where could that be matched? That has to be matched as well. Every vertex of the graph is matched. And so let's say it's matched off to the right here, just to kind of give you an idea of what can go wrong with the doubling tree. The problem is this top node now cannot be matched, right? Which is not possible because we're assuming we have a perfect matching. So that's to show us that no path, no green path alternating could have led us up a finite branch, right? It must have continued on forever. And so none of these places would have been matched, and had we followed the matching up in that direction. And so we know the perfect matching would have to lead us up to, let's say this is the infinite path here. And then going back to the original tree, the edges in the matching represent the path or an infinite path of the tree. Remember, we've assumed the part of the hypothesis of the sigma of sigma 1,1 AC naught was that each tree has a path, but now we're using the perfect matching to define that path. And so, by the way, the reason the doubling tree works is by a parity, right? So it makes all the branches, it makes all the finite branches or paths, I guess, from the root node of even length. And if you start a matching on the first edge and you alternate up an even path, an even number of edges path, you will not be able to I mean, as long as you're alternating back and forth and not missing one, which is exactly what we'd be doing because we have a perfect matching, we would not be able to end the last edge to be in the matching. We'd not be able to have that be in the matching. All right, so this now gives us our path through the tree TK, and therefore we would be able to conclude sigma 1,1 AC0. All right, so I think I'll kind of come to a close. I wanted to mention a conjecture that we think perfect matchings implies ATR naught. So again, climbing up one more level in reverse math, this arithmetic transfinite recursion. We have a partial result in computability theory that codes ordinals or ordinal jumps of sets. And this is an analog of one of the constructions that we found in the Koenig duality theorem project, the paper by Aharoni, Magidor, and Shore. They say that, or they use the fact that it's to prove ATR, to imply ATR naught over RCA naught. They say they show that it suffices to code the logical connectives and the quantifiers. Well, specifically, once you have truth and negation, or at least membership in the set and negation, then you want to code and also there exists. That is sufficient to reverse to ATR naught. There's one problem with induction that we've encountered, and so that's why it remains a conjecture. So I think I will end there.